In this video, we're going to examine two major discoveries that further our understanding of the atom. The first of these was Henri Becquerel's discovery that uranium emitted a type of energy not observed previously. Shortly after, Marie and Pierre Curie observed the same radiation found in radium and polonium. It was the Curies that first coined the terms radiation and radioactivity. Further discoveries identified three forms of nuclear radiation: alpha radiation, that releases a particle with a mass of 4 and a charge of positive 2, beta radiation, which releases a particle with no mass and a charge of negative 1, and gamma radiation, which has no mass or charge and colloquially are called gamma rays. Following this discovery, British physicist J.J. Thomson conducted an experiment involving gas. When a gas is kept in a high-pressure environment, heated, and has an electrical current passed through it, it causes electrons to separate from the nucleus. Electrons are visible in this state, called plasma. Plasma can be seen in children's toys called plasma balls, which contain inert gases kept in a sealed glass ball to keep the pressure high and adds electricity and heat when plugged in to cause the gas to form plasma. If you think that plasma looks like lightning, that's because lightning is also plasma. The important thing is that plasma is visible to the naked eye. J.J. Thomson theorized that plasma would behave in a predictable way when passed close to a strong electromagnet. If atoms had no charge, they would not attract or repel because of the poles of the magnet, and thus plasma would travel in a straight line. However, this is not what Thomson saw. Because the visible part of plasma are electrons, it repelled away from the negative pole and did not travel in a straight line, which is what Thomson saw. From this, Thomson concluded that neutral atoms have equal positive and negative charges. However, Thomson logically assumed that the positive and negative particles attracted to one another, and thus were found together in the nucleus. He used an analogy of a blueberry muffin in which the smaller electrons were represented by the blueberries in a larger muffin, representing the nucleus. However, as we'll see in the next video, this assumption was proven incorrect.